And we are going to choose another example from 4.5. You're going to choose one. Okay. So I would like to continue with this section, 4.4. Okay, ready? Nothing here is new. In section 4.4, we're talking about L'Hopital's rule and the 7 indeterminate cases. We've encountered all of them so far. Okay, but only these two, as you see in the definition of the rule. Suppose that f and g are two differentiable functions and g prime is not 0 on an open interval I that contains a except possibility a, and the limits of f and g, either side or one side, doesn't matter, are both 0 or both infinity. Then we discussed this a long time ago because we needed it. So only then you can determine the limit of f of x over g of x as being the limit of f prime of x over g prime of x. And so L'Hopital's rule works only in these two. These are the other 5 indeterminate cases. 0 times infinity, 1 to infinity, the difference, infinity minus infinity, 0 to 0, and infinity to 0. These are total of 7 indeterminate cases. And I said examples to be chosen in class, and I let you choose. So we are on page 307. Anything you'd like to pick between, or you can look at the ones that are assigned as homework, anything between 7 and 66, and that's what they are. So please choose anything between 7 and 66. They are all triggering L'Hopital's rule, but not necessarily. There are limits that don't require L'Hopital's rule. So I would like to choose. Please choose. If not, I will. We practiced all this. That's why. Which one? 27. Very good. So we have limit x approaches 0 from hyperbolic tangent over tangent x. Okay. When I'm asked to find a limit, what is the first step? I have to plug it in. So then I have hyperbolic tangent. Let's say we don't remember what it is. So hyperbolic tangent, if you remember, is hyperbolic sine over hyperbolic cosine. And we have to remember that this is e to the x minus e to negative x over 2 and e to the x plus e to negative x over 2. These we have to remember. And I simplify when I flip. So this is e to the x minus e to negative x over e to the x plus e to negative x. So when I plug in 0 in this function, which is hyperbolic tangent for the numerator, when I plug in 0, this is 1 minus 1, which is 0. And this is 1 minus 1. And this is, I'm sorry, it's 2. So the answer is 0. So there is nothing I have to do here. Any questions?
So in the event we can't use L'Hopital's rule, we're just calculating the limit?
You don't have to use L'Hopital's rule. If you have a shortcut or an easier method, use the easier method. In this case, you can use L'Hopital's rule unless it's 0 over 0 or infinity over infinity.
Yeah.
So there is no need to do anything. When you plug in 0, you get, in the denominator, you get 1 plus 1. And when you plug in 0 at the top, you get 0. 0 divided by 2 is 0. Good. Anything else? Number? 40. Okay, very good. So let's take a look at 40. And we have cosine x times natural log of x minus a. Everything divided by natural log, e to the x minus e to a. And this is limit as x approaches a from the right. Perfect. Okay. We have to plug in. So this has no problem. This is approaching cosine A. As x approaches A, from either side, doesn't matter, or from the right, it's cosine A. Where does this go? So I have to plug in, because I don't know what to do. I don't know if I need to do anything. What does it approach? You have to remember how to graph natural log. This is the graph of natural log. As x approaches A from the right-hand side, this approaches 0. So when x approaches 0 from the right-hand side, this approaches negative infinity. As x approaches 0 from this side, the function approaches negative infinity. What happens here? It's e to the a minus e to the a, which is 0. It's the same concept. It approaches negative infinity. Since this is not a problem, it's a factor. It's approaching cosine A. I'm going to move it in front as a factor. If I don't, I'll have a lot of work to do. Limit as x approaches A from the right, from natural log of x minus A, divide natural log e to the x minus e to the a. Good. So then what do I do now? So the indeterminate case is infinity over infinity. The sign is not important. So then what would you recommend? So L'Hopital's rule is applicable in both 0 over 0 or infinity over infinity or negative. It doesn't matter. The sign is not important as long as it's infinity over infinity. So what do I have to write next? L'Hopital's rule. Let's read the L'Hopital's rule again. So if in the case of 0 over 0 or infinity over infinity, when I determine the limit of this, I can write the limit. It's only for limits of the top prime over the bottom prime. Only for limits. You can never use this for functions. Okay, so what do I have at the top? 1 over x minus a times the inner function prime, which is 1. Perfect. What do I have in the denominator? Minus e to the a times the inner function prime, which is e to the a is a constant. E to the a is a constant. What is the rate of change of a constant?
0.
Right. So it's e to the x. Very good. So let's continue. I will try to simplify this a little bit. Hopefully I can. So I have limit as x approaches a from the right. This is e to the x over this. So the numerator is 1 over x minus a. This is e to the x over this, and I'll flip. So e to the x minus e to the a over e to the x. Any questions so far?
Let's just one more time explain how it was infinity and negative infinity.
Here?
Yeah.
So natural log is this function. And natural log is this function. When x approaches a minus a is 0. The function values when x approaches 0. X approaches 0, the function values approach negative infinity. In both. So as x approaches a from the right, this is e to the a minus e to the a, which is 0. As x approaches 0, the function values approach negative infinity. Because that's the graph of natural log. Is that better?
Yes.
Okay. So then, because of that situation, I don't want to mess with this. This does not create any problem. When x approaches a, this approaches cosine a. So there is no problem. No undefined case here. Even if it's 0, if a is 0, if we're 0, then this will be 1. So it's still no problem. So I take it out as a factor. I'm not going to multiply this and use the product rule, because that will never end. And this is a constant. That's why I went outside. So then I have infinity over infinity. I differentiated the top, 1 over x minus a. I differentiated the bottom, and I get this. Are we okay so far? So now I have a fraction 1 over x minus a, but this is e to the x over this, so I have to flip it, and I did. Is this step clear now? Yes or no? Do we see it? Are we convinced, or we are not sure? So then, there is no need for calculator, so I'm just flipping up the denominator. So that's fine. So I copy the numerator and I flip the denominator. So now the new function is, or the new limit is, e to the x, oops, I didn't mean that, over e to the x times x minus a. Now let's analyze this again, so I know how to continue. Okay. So the numerator approaches what? Okay. So x approaches a from the right, e to a minus e to a. Perfect. X approaches a from the right, 0, a minus a. Perfect. Good. But now I have this factor, which is a friendly factor. When x approaches a from the right-hand side, this approaches e to a. I don't want to mess with it. It will come out as a factor. Because again, if I have to differentiate, that will never go away. So I'll have a run into difficulties, and it's just a factor. It doesn't create 0 over 0. It doesn't create infinity. It's just e to the a. So now I will differentiate the top, and I get e to the x. I will differentiate the bottom, and I get 1. So then I have cosine a over e to a, and how much is this? Thank you. Which goes away as 1, and the answer is this. Very good pick. Any questions?
Could we safely assume that we have to bring the fact out up front? Might be that answer?
No, absolutely not. Not on a function like that. On a rational function, if I see that x approaches infinity and I have a leading coefficient of 1 and the leading coefficient of 5, then I will say it's 1/5, but they have to have the same degree. I wouldn't. Good. Anything else we would like to pick? Any other problem here on page 308? I would like to pick something from 59 through 66 and another problem if you want, and move on. You want 59? Very good. So 59 on page 308, and we have limit as x approaches 1 from the right, x to 1 over 1 minus x. Yes, it is 1 minus x. Good. Perfect. What now? We're asked to find this limit. We worked on these limits some time ago, before test 2. Okay, so what do I have to do next? Yes, where does this go? Infinity, indeed, because the denominator is 0. I cannot have 1, because it's 1 over 0. So that has to be one of the indeterminate cases, like infinity, negative infinity, or DNE. So 1 from the right, this will be 1 from the right will be 1.1, so it's negative infinity. And this approaches 1. So the situation is 1 to negative infinity, or 1 to infinity. It's the same thing. Still 1 to infinity. Okay, so then what do I do? How do I proceed in this situation? This is not a L'Hopital's rule case. And remember, we can go back to the list of 7 indeterminate cases, and it's this one. It's one of the most difficult to work with. This, and this, the powers, are one of the most difficult ones. Good, so since it's a power thing, like 1 to infinity, what do I have to do no matter what? I will say let y be x to 1 over 1 minus x. And then this should give you the hint of what I need to do next. Natural log. So natural log y equals 1 over 1 minus x, natural log x. I will rearrange this a little bit. So then natural log y equals natural log x over 1 minus x. Okay. Now what do I do as the next step? And we've done this with several problems some time ago. We did not have this situation on the test, but we will have it on the 3rd. Apply the limit to both sides. Very good. So then I have limit as x approaches 1 from the right equals limit as x approaches 1 from the right. Excellent. Although this is not what we are asked to do. We're not asked to find the limit of the natural log. But then, under certain conditions, what are we going to do with these two operators, the limit of the natural log? Swap them. Yes. Very good. So then, now I look at this. I plug in again. Tell me what we have at the top. Tell me what we have at the bottom. When x approaches 1. Very good. Over. It's 1 minus 1. Good. So then, is L'Hopital's rule applicable here? Yes. Very good. So then I have limit. So x approaches 1 from the right. What is the derivative of the top? Very good. What is the derivative of the bottom? Excellent. So then the limit is? Excellent. So now I'm going to copy the front and the first step and the last step.
Wait, I have a question.
Yes.
So the limit from the natural log of y and
Yes.
the limit from the natural log of x.
Yes. I apply the limit to this side and I apply the limit to this side.
Okay. Gotcha.
So now I will copy the first and the last step. So I have limit, so x approaches 1 from the right, from natural log y equals negative 1. What will be our next step? We already talked about it, but just say it to me again, please. Anyone? Yes, swap the operators. So I can put natural log in front of the limit. Because these functions are continuous. That's the condition. And I can do this. So then natural log of the limit of y as x approaches 1 from the right is negative 1. Now the question is, what is this? Natural log of what will be negative 1? Let's talk about what is the natural log of what is 1 first, and then we'll figure out what negative 1 would be. if we had here just positive 1, what you would have said? Natural log of blah is 1. What is the blah? Say it again. Natural log does not exist at 0. It has a vertical asymptote. I can never plug in 0 in natural log.
E.
E. Very good. But I don't have a positive 1. I have negative 1. So if I had positive 1, this would have been E. Natural log E is 1. But I need something else so I can get negative 1. Natural log e to negative 1. Indeed. Indeed. So then I found the answer. Limit as x approaches 1 from the right, from, what was it, x raised to 1 minus x equals 1 over e. Very good. Any questions for me?
I just have a question about
Yes.
this process.
Yes.
I mean, it's probably just me, but I find a lot of this pretty challenging. And with that being said, you know, having these problems for homework, I'm not confident in my ability to be able to get the majority of these correct.
Have you looked at the previous problems that we did before test 2?
Yes.
Okay.
Yes. I mean, like, well, that being said, how do you suggest then when like we're trying to, I'm trying to complete this assignment, or if I get stuck on like 4 or 5 in a row, what do you think I should do?
Redo the problems we did in class step by step several times before you even look at the homework.
Okay.
So I would not attempt the homework before I know for sure that I can reproduce this 1 or 2 examples on my own. And then I'll say, now I'm ready to try.
Okay.
Because the answers are in the back of the book, so I have an indication whether I'm on the right track or not.
Okay.
But I will redo these step by step several times.
Gotcha.
Yes, Thomas?
By continuous, do you mean like around 1?
Yes. But the functions themselves have to be continuous. Very good question. So if you remember, in this handout, we looked at this very important theorem, and I said we're going to use it in chapter 4. Okay? F is continuous, a continuous function at b. You're right, at 1. If the limit, if the limit of g of x from either side of a is this, then I'm allowed to swap. So this also has to happen. If you read the theorem one more time, you'll see. So how do I get it? By simply swapping the 2 operators. So all these steps go together. But the function has to be continuous, and this limit has to be true. So this was a theorem that we talked about in chapter 2. It comes in over and over, and it allows us to swap the operators. You see here, so f is inside limit, and now he's outside of the limit. So imagine this is natural log, right? Or it was initially natural log in here, and you said correctly to move it in front. So this was function natural log, and I moved it in front. So now it's natural log of the limit of the function g. And that's exactly what we discussed. That's why I put it here. I didn't discuss it a lot in chapter 2 because there was no application there. But then I put it in and I said, please be careful with this, because it's a very useful result. And it will help us a lot. And this is one case, one example. Very good question. Thank you. Okay. So let me know on Wednesday if you still have difficulties with this. But please redo this problem, or if you want, we can choose another problem and work on it right now. But again, without practicing before you attempt homework, it's not going to help much. So would you like to pick another? I don't have any problem with that. Yes. 51. Yes. Limit as x approaches 0 from the right, from 1 over x minus 1 over e to the x minus 1. Perfect pick. So don't write this, please, what I'm going to write next. Yes or no? If I said not to write it, obviously it must be no. The reason why is no. I would like you to explain. Yes. True. In other words, the condition from chapter 2 that we know of, let me go back to the handout so I can show you. I should have not put it away. No, it will take me 3 minutes to find it, right? Okay, no, I got it. Okay. So if you remember, one of the most important concepts here is about calculating limits using limit laws. And there are 11 limits I said. I did not list them here, but I said the limit of f has to exist and the limit of g has to exist. So good pick. The limit of f doesn't exist. The limit of g does not exist. So the limit laws are not applicable here. I can't do that. I cannot split it like this, although I wish I could. I can't because this is positive infinity, and this is whatever else. I don't care. If one of them is undefined, I can't do it anyway. Good. So there must be something else that needs to be done or we can apply here. Any suggestions? How to proceed? What can you ever do with two fractions? Find, right. What is the least common denominator? Perfect, excellent. Thank you very much. Next step. What does this need? What does this need? Good. I'm ready to plug in now. I couldn't do it before because it was infinity minus infinity or whatever else, so I couldn't do anything. So the top goes to, very good. The bottom goes to, perfect. That's a good case. See, I cannot consider this a factor because it's 0. I cannot consider this a factor because it's 0, so I cannot take anything out in this case.
So you have to differentiate it that way.
Using L'Hopital's rule, because it's 0 over 0, yes, there is no other way. So give me the derivative prime, the function prime.
That's e to the x minus 1.
Perfect. Now the denominator, careful because it's a product. So I have to differentiate to use the product rule. The first function prime, so plus the first function times the second function prime. What is the second function prime? Excellent. Good. I'm trying again. Nothing goes away. I cannot, don't try to simplify anything. So now I'm trying again. Yes?
When you do this, when you do the top, you just do the top alone, you don't, it's not a function, it's not a function.
In the case of a ratio, if I get 0 over 0 or infinity over infinity, and this is the only case in which I'm allowed to do that, I go right ahead and write the limit of the top prime over the bottom prime. Good. So now, where does the top go? Where does the bottom go? Very good. So then limit, as x approaches 0 from the right, the numerator, perfect. The denominator, what is this? Good. What is this prime? Plus, this is a product. Plus. Yes. So e to the x plus x e to the x. What will I do next? Look at this ratio and say, oh, I know. You're going to there is nothing I can combine. Oh, other than, oh yeah, I see e to the x and e to, but I was expecting something else. Sorry about that. You're right. Exactly. Don't forget what you want to say. One second, Ian. Sorry. Of course. What is the limit? Very good. Yes, Ian, go ahead. Yeah, I just didn't, as you saw, I wrote them a little fuzzy. Yes, but I was just wanting you to say factorial e to the x to get rid of it. Hold your thought. Yes, Ian.
So, you guys at the part you did the red in it, right? You don't continue, how do you want not to continue to differentiate? You could differentiate e to x to e to the x, and you could
I can differentiate only if I have 0 over 0 or infinity over infinity.
but that wouldn't still be 0.
No, because when x approaches 0, e to 0 is 1. I can differentiate because I want to differentiate. So I can only differentiate in the case of 0 over 0 or infinity over infinity. If I have the case of 1/2, I'm not differentiating. I'm not allowed to.
I just forgot that e to the x.
Yes, yes, yes.
So right before the red marker issues, the step above that, where can we just plug in 0 at that point?
Yes, of course.
Okay.
Absolutely.
And then I actually have one more question.
Yes.
About the very first problem we did, number 27.
Yes.
When we get 0 over 2, isn't 0 over 2 just for the numerator, and then that
Let me take a look.
0 and then.
Let me take a look. Where are we?
Number 27. It's the
Oh.
very first problem that we did. And then that.
Okay. You're right. I forgot about this. I only looked at this. You're right. I'm sorry.
No, I just wanted to make sure I understood it correctly. That's all.
You're right. I'm sorry. Yes, I looked at the fraction and I omitted it. Yes, I have to do that again. I'm sorry. 27. Sorry. So limit as x approaches 0 from hyperbolic tangent over tangent x. So this is indeed 0 over 0. Thank you, thank you, thank you, thank you. Sorry about that, my mistake. Yep. With all my colors, I didn't see colors anymore. Sorry about that. Thank you. Very good. So then if it's 0 over 0, then I go back. So let me also cross it out, not just say sorry, because this is what I have to do. Everything else is fine, but I didn't finish it. Okay, so now because we have a 0 over 0, we will differentiate the top or we differentiate the bottom. My apologies. Thank you. So now we differentiate tangent, and we remember tangent, hyperbolic tangent prime is hyperbolic secant squared, and tangent prime is secant squared. So now we plug in 0. The denominator, remember, is secant squared of 0. Secant squared is 1 over cosine, and cosine 0 is 1, so this is the denominator is 1. And now we have to identify and see what a hyperbolic secant squared is, which is 1 over. So hyperbolic secant squared x is 1 over hyperbolic squared hyperbolic cosine squared x. So this is 1 over e to the x plus e to negative x over 2, everything squared. or 2 over e to the x 2 squared over e to the x plus e to negative x squared. Or if you want 4 over e to the x plus e to negative x squared. Perfect. So now when x approaches 0, this is 1, this is 1, because 0 here, e to 0 is 1, e to 0 is 1. So 1 squared, 1 plus 1 is 2, 2 squared is 4, 4 over 4 is 1. So the top is 1, so the limit is 1. Thank you. Sorry about that. Any questions? Is there anything else that you would like to go back to in L'Hopital's rule? Okay. So this is all together. We have done all this, and I don't remember, we already solved one of these problems and so on and so forth, and maybe this one or something similar. What I would like to work on, at least, it's up to you if you would like to work on any of those problems, but I would like to work on a problem with a horizontal asymptote, because we did not get the chance to look at that. So on page 317, I'm going to see if I can find one. If not, I can make one up. Yes, on page 318. Please choose 65, 66, 67, 68. Any of those problems, because I would like to show one function with slant asymptotes.
68.
68, very good. So y equals x to the third over x plus 1 squared. Okay, very good. Ready? So for this function, we're asked to do everything from scratch. Can anyone give us, what is the first step? What is the very first step? Always. The domain. So what is the domain of this function? Yes. Not equal to -1. If the function is undefined at -1, so will the first derivative and any derivative therefore thereafter. Good. So knowing that, I already know that I have to determine the x and y-intercepts. Is this function ever 0? A ratio is 0 when the top is 0. Under which number? 0. How many solutions x equals 0 do we have when we solve the equation blah 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 equals 0? So if I write the equation x to the third over x plus 1 squared equals 0, I get that x to the third must be 0. So I have how many solutions? 3. What do I know from pre-calc? When a function has a solution that has a multiplicity 3, what type of point would that be? Remember x cubed. X cubed. Yes, but slowly. Okay, correct. So it will cross, but very slowly. What type of point will that be? Which we will determine it in a minute. Inflection point. It's exactly like x cubed. Very good. We'll see that in a moment. Perfect. So now I need to determine this, 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 and this. Obviously, x equals -1 must be what? a vertical asymptote. Very good. So now, when x approaches infinity, which of these two, top or bottom, will be the strongest? Top. When x approaches infinity, then the limit of this function will be infinity. The bottom is always positive. Very good. So I'm going to write this, what I just discussed with you. So limit of y as x approaches infinity equals infinity. Now limit as x approaches negative infinity of y. Let's see. The bottom is still smaller than the top, and it's always positive, no matter what. So when x approaches infinity, where does this whole thing go? Negative. It's to the third power. This is positive, but this will be negative infinity, right? So this will be negative infinity. So negative infinity and infinity. Now I need the limits left and right of -1. So limit as x approaches negative infinity from the left of x cubed over x plus 1 squared, and limit as x approaches -1 from the right of x cubed over x plus 1 squared. When x approaches -1, the top will approach when x approaches -1, x to the third will approach -1. And the denominator, -1, from the left or from the right, it doesn't matter. This will be 0, positive. So 0, positive. So what should be this and what should be this? In both sides cases. Yes, very good. There is nothing else we can find about the function from the function itself. I can move again forward to what? What am I trying to find now? Very good, f prime of x. The top prime, 3x squared times x plus 1 squared minus x cubed times 2 times x plus 1 over x plus 1 to the fifth. Let's stop for a moment and see if this is clear. Is this clear? The top function prime, 3x squared times the denominator, minus the top function times the denominator prime, over the denominator squared. Agreed? Okay, what is the key word now? Super important. Yes, what will I factor out? Definitely an x squared and definitely an x plus 1. Let's see what is left. From here I have removed an x squared and I removed an x plus 1. So I have 3 times x plus 1. Do you agree with that? From here I removed the x plus 1. I removed 2 of those, so I still have negative 2x. Any questions? Any questions? Are we okay? Please ask any questions. Anything? You okay? Is it a yes? Is it a no? Okay. So then one of these two will go away. I still have x squared and I have to combine like terms inside. 3x plus 3 minus 2x over x plus 1 to the third power. So this is x squared, and this is x plus 3 divided by x plus 1 cubed. Now, I have to look at the first derivative. I have to find its critical numbers and study the sign, and then I can move on to the second derivative. So, now, for simplicity, I recommend just for the sake of the sign, just rewrite it like this. Just for studying the sign. Because I don't want to spend too much time, and I don't want to spend any time on this. What is the sign of this? Right. So the sign will be given by this expression, not by this expression. So, first of all, critical numbers. Can anyone give us critical numbers for this function? 0 and? Very good. So when you set this equal to 0, you get x equals 0 and x equals -3. What about critical numbers coming from f being undefined? F prime being undefined, sorry. But f prime is undefined at -1, but so is the function. So that cannot be a critical number. A critical number has to make the derivative undefined, but the function exists. But the function doesn't exist at -1. So -1 cannot be a critical number. So I will have to put 0 and -3. So now I study the sign only for this expression. This, don't bother with it. Don't plug in anything in this one. Only here. Okay. Let's say -4. -4, -4, positive, because both are negative. Let's say -2, positive and negative. Let's say 0.5, positive. I'm sorry, what am I doing? -0.5. -0.5, I said 0.5, but I showed here. So -0.5, positive. 10, positive. Very good. I have to determine this point here when x is -3. I have it when x is 0, but when x is -3. I go back to the function, and I get -27, -3 plus 1 is -2, 2 squared is 4, -27 over 4. What is that? -27 over 4 is -6.75. Correct me if I'm wrong. Is it -6.75? Okay, perfect. So now I'm trying to make sure that these two rows work in sync. I'm trying. So from -infinity to -6.75, the function increases. Does the sign of the first derivative support that? Good. From -6.75 to -infinity, the function decreases. Does the sign of the first derivative support that? From -infinity to 0, the function increases. Does the sign support that? Of the first derivative, yes. And from 0 to infinity, does the sign support that? Any questions so far? Now I would like to establish whether this function has max-min. Does it? Is 0, 0 a point of max or min? No, because the first derivative is 0 there, but it does not change sign. So this point cannot be a max or a min. Okay. Is -3, -6.75 a max or a min? Yes, because the first derivative is 0, and it changes sign there. So this will be a local max, for sure. This point, -3, -6.75, local max. Good. I already know that it will definitely have an inflection point at 0, but let's study this second derivative. Okay, so here's the second derivative, the first derivative, I'm sorry. I will distribute x to the third plus 3x squared over x plus 1 to the third. This is what I will differentiate. To find the second derivative, top prime, 3x squared plus 6x times the denominator minus x to the third plus 3x squared times the denominator prime over the denominator cubed squared. We already discussed that since the solution x equals 0 appeared 3 times. If I don't get the inflection point from whatever I'm doing, you chose the problem, I haven't even looked at this. If I don't get x to be 0 as the inflection, the x coordinate of the inflection point, I know something is wrong. Ready? Okay, the key word here is obviously what? X plus 1 to the second power. So let's see what is left. I have an x plus 1 left here. I have to distribute here. So x, let me think for a second. If I factor a 3x, I have x plus 2. Yeah, I can factor anything else. Okay, I have to work it out. So x plus 1 times this, 3x to the third plus 6x squared plus 3x squared plus 6x. This is out, and I have to distribute negative 3. Minus 3x to the third minus 9x squared. So an x plus 1 from here multiplied by this. X times 3x squared, x times 6x, 1 times 3x squared, and 1 times 6x. This is gone, so I only have to distribute 3 with minus in front. Minus 3x cubed minus 9x squared. I'm hoping that some terms will go away, hopefully. Let's double check here what's happening. Nice. This is nice. And this is nice. 6x squared plus 3x squared with negative 9x squared. 3x cubed with minus 3x cubed. Excellent. It couldn't be nicer. What is the sign of this expression no matter what? And I'm not going to bother with it. Good. So f double prime equals 0 obviously means x equals 0, as we knew from the moment we found the x-intercepts. We knew that. So then I have 0 here. So I'm studying the sign only for x. X to the left-hand side will be, left-hand side of 0 will be what sign? And to the right-hand side of 0, it will be so obviously 0, 0, as we knew from the get-go, is the only inflection point. Well, I shouldn't say the only. I know now it's the only, but then I didn't know that it was the only. Any questions? And now we're ready to graph this function. I'm kindly asking you to adopt a chart, any chart you want, and summarize the information, because looking at 4 pages is going to be almost impossible to put the information together. I'm not saying that my chart is the best. I'm saying use your own. You can put this in any order. I prefer putting the function in the middle so I can have top and bottom. If I reverse these two, then it's kind of difficult for me to look at these 2 rows and interpret the top one. So I'm looking at these 2 and I'm interpreting the middle one, so I don't forget anything. But you feel free to invent your own. Okay, so based on the chart, I'm going to graph the function. It's not symmetric. It has, oh, one thing. I just said why I chose that function, right? I asked you to choose one. And I forgot why we chose that. This is 11. Okay. With a rational function, with degree n in the denominator and degree n plus 1 in the numerator, which is this case. What is the degree of the top? 3. What is the degree of the bottom? 2. So degree of the top is 3, the degree of the bottom is 2. The degree of the top is by 1 unit larger than the degree of the bottom. This is the requirement for a slant asymptote. Because when I divide degree 3 by degree 2, what degree will I get? A line, which is degree 1. So I need to find, so again, as an example, degree 3 over degree 2. 1 more than the degree of the denominator. This always result in no horizontal asymptote ever, but slant asymptote. Now I have to find the slant asymptote. So I have y equals x cubed over x plus 1 squared. This is one time in which I will expand the denominator. So x to the third over x squared plus 2x plus 1. And I have to divide x cubed by x squared plus 2x plus 1. And then I have to come back and graph it. Okay, so x squared times what is x cubed? X. I have to go back and distribute to all three. X times x squared is x cubed. I have to subtract. X times 2x, 2x squared. I have to subtract. And x times 1, x, I have to subtract. Negative 2x squared minus x. X squared times what is negative 2x squared? Negative 2. To go back, negative 2 times x squared is negative 2x squared plus. Negative 2 times 2x is negative 4x plus. Negative 2 times 1 is negative 2 plus 3x plus 2. And I cannot continue beyond this because I can't find an answer for x squared times what is 3x. So this function can really be rewritten how? Yes, Thomas? The quotient, yes, yes, plus
the 3x.
remainder, very good, over, and now I'm going to condense it and write x plus 1 squared. Excellent. So we use the long division to divide x cubed by this. Only this, y equals x minus 2 is the slant asymptote. Why? Because at infinity, the function will approach this line and this will approach 0. That's why. So now we can go back, and next to the chart somewhere I make myself a note. Y equals x minus 2 slant asymptote. And now I do have all the information needed. So when we graph a function with asymptotes, what do we have to graph first? The asymptotes. Let me